So this section is called Solving Problems with Trigonometry, or Trig in Real Life. We will also in this packet be discussing the law of sines and cosines, but not until next time. Now we're going back to using trig the way we did, probably more like how you used it in geometry, but we're going to make it a little bit more complicated because there are more things we can do with trig. At the beginning of these notes, we have the review of the basic trig functions, as well as, what is defined as opposite, adjacent, hypotenuse to an angle. We've already seen those. We should feel okay. We're going to keep going. So level 0 problems for this. We've actually already done problems like this way back when on like section 4.2 or something like that. But this is like the basic level of what we're going to be doing by the end of today. So we're going to solve the triangle ABC for all its unknown parts given A is equal to 32 and B is equal to 17.3. Remember that capital letters here represent angles and lowercase letters represent side lengths. That's going to be the same throughout. Capital letters or Greek letters could be angles. So if they told us A is equal to 32, that means we're looking at this angle right here. This is 32 degrees because that's A. They also gave us that side length B is 17.3 units. We want to solve the rest of the triangle. It feels like they didn't give us enough information, but they totally did. Because isn't C 90 degrees? Which means what is angle B? 58. Because angle B is going to be 180 minus angle A minus angle C. Which, yes, 180 minus 32 minus 90 is 58. So we have all three angles. Check, done. We also can use basic trig to find the missing side lengths. Because remember, if we have, let's say our angle, the theta we're going to use this whole time is going to be 32. We're going to keep using that one. We want to find the opposite of it. And we know the adjacent. So what trig function can I use combining opposite and adjacent? Tangent. So if I do the tangent of 32 degrees, make sure you put a degree symbol there or else you're using radians. The tangent of 32 degrees should be equal to the opposite, which is side length A, divided by the adjacent, which is 17.3. We just need to solve for A. How do we solve for A? Yeah, multiply 17.3 times tangent of 32 degrees. Like I said, this should look familiar. We've done this before. At this point, you turn to your calculator. And for me, for most of this entire packet, we're going to round to 2 decimals the whole time. Sound good? So make sure your calculator is in degrees. Then you can do this calculation. On the mode button, the third option is between radian and degrees.
And change it to degrees.
Highlight degree, press enter, and then you can quit that screen. So 17.3 times the tangent of 32 is A. That means that A is equal to 10.81. I'm going to go ahead and label that because that's a nice way to say we found all the sides. What's the missing side length here?
Hypotenuse.
The hypotenuse. Now, kind of the world's your oyster in how you find the hypotenuse. I like sticking with the same angle the whole time. So we're going to keep looking at this angle C. Obviously, this is hypotenuse, but now that we know both the opposite and the adjacent, we can use either of them. I would use the one they gave you because you haven't had to round that number. So which trig function combines the adjacent and the hypotenuse? Cosine. So we're going to set up another trig function that says cosine of 32 degrees is equal to the adjacent, which is 17.3, over the hypotenuse, which we've labeled as C. This time to solve for C, you're going to have to multiply by C on both sides. It's going to be C times the cosine of 32 degrees equal to 17.3. And then to continue to isolate C, you divide both sides by cosine of 32 degrees. And once you have it set equal to C, you can throw it in a calculator. I would get used to using the fancy fraction because it will be very helpful with things we're doing next class. 17.3 divided by cosine of 32. We're going to round to 2 decimals this whole time, which would be 20.40.
Well, you need a for your calculator thing.
Bless you.
Right?
Yes, it should be in degrees. We're going to be working in degrees basically for these, bless you, for these kinds of problems here on out. So that's a level 0 problem because we've technically done this before. Because this lesson is labeled solving problems with trig. These problems are problems that occur in real life. So some real life applications of trig are what we're going to go over today. The reason you see Washington's face right here is because we are going to utilize something called an angle of elevation and angle of depression to be able to graph and create pictures that will be able to be solved with trig. Yes? So if you look at this graph right here, you have an angle of elevation graph. It's a picture. An angle of elevation means how much higher than eyesight something is. So if you notice these people, they're standing a certain distance away from Mount Rushmore and they're looking up at Mount Rushmore. The angle with which they have to look up at it to see the top of it, that is an angle of elevation. On the other hand, what's called an angle of depression is looking down. So this guy is standing at the top of what I assume is some sort of canyon, I guess. And he's standing like this and then he looks down to see the boat. Straight out from his eyesight would be level. So what angle he looks down to see the boat is called an angle of depression. Does that make sense, the difference between them? Okay, cool. Some helpful steps for the problems we're going to do in a second. Number 1, draw a picture to represent a situation. It's not going to make sense till you have a picture drawn and labeled. You label the right triangle or whatever triangle you get correctly. Find the trig function that will help you solve the problem, and then solve the problem. Yes? Here's the problem we have. It says, an angle of depression of a buoy from the top of the Bay Lighthouse in New Jersey, 130 feet above the surface of the water, is 6 degrees. Find the distance x from the base of the lighthouse to the buoy. So let's say you get a job at a lighthouse. So we draw a lighthouse. You don't have to be an artiste, but it does need to kind of look like a lighthouse. Here's my lighthouse. Okay, it's not a barber thing. Here's the top of the lighthouse. Okay, and the lighthouse is on some land. Okay, and then, well, let me make it look like a cliff. And then there's some water. Keep complimenting. Okay. Okay, noted for next time. In this water, there's some sort of buoy. A buoy is like a floating object in water. It usually tells boats lanes to go through. We don't really live near water, so you may not be comfortable with water vocabulary. But what has happened here is we said that the lighthouse itself is 130 feet tall. So we've labeled it. And that the angle of depression from the top of the lighthouse to the surface of the water to the buoy is 6 degrees. So we have straight. That's straight out from the buoy, correct? Or from the lighthouse. Well, if we look at that buoy, this angle of depression is going to be 6 degrees. Let me label that with purple. That is 6 degrees for my angle of depression. That's what, from compared to straight out, I've looked down 6 degrees to see the buoy. We want to find the distance from the base of the lighthouse to the buoy. Okay, well, if I do this, and I do this, what have we created in this problem? A right triangle. What am I trying to find out here? Am I trying to find out this distance? No, I already know this distance. What is that? That's 130. What am I trying to figure out? The distance, this direction between the lighthouse and the buoy. Not the direction, like how long I'm looking, but the distance left to right between the lighthouse and the buoy. Okay, because we drew a nice picture and we've labeled it correctly, We see that we have an angle. We know that angle's opposite side, and we want to know the angle's adjacent side. What trig function do I use? Tangent. I'm going to find the tangent of 6 degrees. Oop, that's a whole 60. 6 degrees. And it should be equal to the opposite over the adjacent. One variable I can solve. First, we derive the formula for x, so don't do the tangent of 6 first. Do that at the end. If you multiply by x on both sides, it's going to be x times the tangent of 6 degrees equal to 130. Keep solving for x. We'd have x equal to 130 divided by tangent of 6 degrees. And that's something you can throw in a calculator. Again, for me today, go ahead and save 2 decimals every time. We should have gotten 1,236.87, what are we measuring in? Feet. Because here's the other thing. With these real life problems, you have to give me real life answers. If you tell me 1,236.87, I'm like, cool. Actually, how far away is the lighthouse? You got to tell me units.
Bring science into it.
Oh, math is science and science is math. You got to label your units, especially when units are given.
Okay, tell me.
Questions about this one, because this is still kind of like level 1 style questions here.
So how does it go up to?
Huh?
What does it go up to?
4, 5. 5. We're going to do a couple more level 1s. But they get progressively harder level 1s.
The level ones just add up to 5.
No. Here's the next level 1 question. Again, it's going to just use basic trig. That's why it's level 1. So from the top of the 100-foot, I don't know how to say the name of this hall, on the University of Illinois campus, Altgeld, a man observes a car moving toward the building. If the angle of depression of the car changes from 22 degrees to 46 degrees during the period of observation, how far does the car travel? Makes no sense till we draw a picture. So first, let's draw the building. It's 100 feet tall. Here's my building. Thank you. There's going to be 3 windows on each of them. I don't know. It's a dormitory. And then I got tired of doing that. So okay. There's my building. Somebody is at the top of this building and they're looking down and they see a car. Here's the first car. Yes, that's my car. Don't judge it. Okay. So we've looked and we've seen this car. What does the problem say is the angle of depression for that first car? 22 degrees. It says it changes from 22 to 46. So the first time we see the car, we were looking at an angle of 22 degrees. Okay, then the car is moving toward the building, so it moves a little bit. Here's car number 2. It's the same car, but it's moving this way. Okay. And we look again, and this angle is 46 degrees. Bless you. Let me go ahead and use the color here. I think that might be helpful. That's the only information it gives you, except for it wants to know how far did the car travel. Okay, wow. I'm looking for this distance here. How far did the car travel? Here's what I know. I know that this can be a right angle if I do this. Here's a right angle. And this can be a right angle if I do this. So I have 2 triangles created here. Let's solve both of them so that we can figure out the difference in the distance between the building and the car. Now I need to label one more thing I forgot to label. What else should I label on here? The height. What is the height of this building? 100. So that angle or that side right there is 100. Yes, it's the building, but I'm labeling it on my triangle side so that it's useful. Let's go with the smaller triangle first. So what I'm looking at, I'm going to highlight it. I would not highlight yours because it'll get really messy. I'm looking at this triangle here. Okay. Whew. I want to know this distance x because I want to know how far away the car was when I first looked at it. What trig function should I use? Tangent, because I know the opposite and I want to know the adjacent. So I know that the tangent of 22 degrees, let me do this in red so it's all the same color. The tangent of 22 degrees is going to be equal to the opposite over the adjacent. If I derive this formula for x, the formula would be x equal to 100 divided by tangent of 22 degrees. We should get a little bit faster at that, put it on my desk, at that deriving. If you don't know where that came from, it's the same steps as the problem right above it. But that's something I can put in a calculator. 100 divided by the tangent of 22 is 247.51 feet. Feet? Yes, feet. Great, that's the red triangle. But I also have a whole other triangle on here that I need to solve. I have this triangle. What's the height on that section? It's still 100. Yeah, that didn't change. And I still want to figure out this distance x. So I'm going to use the same trig function. I want to find out the tangent now of 46 degrees when it's equal to 100 over this distance x. Solve for x, you'd multiply and then divide. It would be x equal to 100 over tangent of 46 degrees. And 100 divided by tangent of 46 degrees is 96.57 feet. But what's the actual question here? How do I figure that out? Subtract, very simple. So I'm going to take the actual distance d between the two cars would be 247.5, I can't see my own handwriting, 51 minus 96.57. We should get that the distance between these cars is 150.94 feet. So check out that. We just answered a real life problem using trig.
By the time the car gets to the building.
You gotta get really fast with your trig measurements if you're gonna actually do this in real life.
Hear me out.
Hear me out.
I'm going to figure out how far a car...
Okay. Question 4. It says, a large helium-filled penguin is moored at the beginning of a parade route awaiting the start of a parade. Two cables attached to the underside of the penguin make angles of 48 degrees and 40 degrees with the ground are in the same place as a perpendicular line from the penguin to the ground. There's a figure for this one. We don't have to draw it. If the cables are attached to the ground 10 feet from each other, how high above the ground is the penguin? I'm sorry. So here's what we know. We were told that this first triangle, the angle is 40 degrees. And that this angle is 48 degrees. I know it's those because the second angle has to be higher because the angle to reach the penguin would be higher. And we want to know how high the penguin is. We don't know this. The only other piece of information we have is that the two cables are tied 10 feet away from each other. Doesn't really feel like enough information, and it really isn't, but it's still a problem we can solve. Let's set up our tangents the way we had been doing. If I was using the blue angle, the tangent of 48 degrees would be equal to the opposite, which I've labeled h, for height, over the adjacent, which is going to be this distance right here. We'll label it x. That's two variables in one equation. I can't solve it yet. So we look at the red triangle. If I look at the tangent of 40 degrees, that's the larger triangle altogether. Still the right triangle, not the like little skinny, oddly shaped one. Still the right triangle, but with the red angle. The opposite is still the height of the penguin. But what is the adjacent side length? Not just 10. 10 plus x. Because we have the distance x from the blue one and 10 more feet since we know they're moored 10 feet apart from each other. Okay. Not great because we don't have any specific values, but do you see how both of these equations use h's and both of these equations use x's? This is a system of equations with trig. This is cool. Okay, so what we're going to do is we're going to solve or derive these formulas for one variable in general, set them equal to each other, essentially doing a substitution problem, and solve for all the things we need. What I mean by that is, you multiply by x on both sides. Now I have this isolated for h. I'm going to do the same thing in the red equation. I'm going to isolate it for h, which means h would be equal to 10 plus x, in parentheses, times tangent of 40 degrees. Well, now those two things are both set equal to h, right? And if they're equal to the same thing, they must be equal to each other. So we change this formula and we now say, well, x times the tangent of 48 degrees must be equal to the red equation. Because they're equal to the same letter, so they must be equal to themselves. Ignoring the top two lines here, if I just look at this equation right here. How many variables do I have? One type of variable. They're just x's. A single variable in one equation means you can solve it. So we need to solve for x. Here's how we do this. Use your small handwriting, if you will. First things first, we need to distribute this tangent. So it's going to be x times the tangent of 48 degrees equal to 10 times the tangent of 40 degrees plus x times the tangent of 40 degrees. I want all of the x terms on the left side. How do I get this on the left side? Well, right now it's added, so subtract. Okay, so then we'd have x times the tangent of 48 degrees minus x times the tangent of 40 degrees. Those are not going to cancel each other out. Equal to 10 times the tangent of 40 degrees. I've just subtracted it from one side to another. This might be ringing your spidey senses for something familiar. We did this with logarithms forever ago. Do you notice that both of these two terms have an x in them? We're going to factor out the x. Take the x out, it goes in front. The leftovers go in parentheses, which is tangent of 48 degrees and negative tangent of 40 degrees. I'm so close to getting x by itself. What do I do to get x by itself? Do what?
All those cancel out.
I divide them. Nothing cancels out. So there's no sort of canceling when there's a plus or a minus in the denominator. My math teacher growing up called that killing cats whenever we did that, and we were to avoid that at all costs. Please don't do that. I know, so avoid it. Well, that right there.
I die on my road because there's so many.
There are now only numbers in my equation, which means we can type that in the calculator. 30.9, and we're going to leave two decimals even if it's zero, so 30.90, yeah. 30.90, what are we measuring in? Feet. Okay, that's x. That doesn't actually answer the question though, because remember, the question was, how high above the ground is the penguin? But now we can use tangent because now we have a value for this x You could use either of them, but using the blue equation where there's not extra plus 10 on there is going to be significantly easier. Okay, so what we're going to do is we're going to take that blue equation. The tangent of 48 degrees is going to be equal to h divided by our value we just got, 30.90. Whew, we're back to a normal looking level 1. What do we multiply? What do we multiply both sides by? 30.90. So our value h is going to be equal to 30.90 times the tangent of 48 degrees, which, phew, is something I can throw in my calculator. 30.90 times the tangent of 48 degrees. 34.32 feet.
No, buy more paper.
A U.S. Coast Guard patrol boat leaves Port Cleveland and averages 35 knots, which is a nautical mile per hour, traveling for 2 hours on a course of 53 degrees, and then 3 hours on a course of 143 degrees. What is the boat's bearing and distance from Port Cleveland? We are not comfortable with boat terminology because we live in a landlocked city. So let me help you out here. When we are talking about knots, that is talking about how fast something is going. So that's a velocity. So these right here, these numbers for 35 knots, that's a velocity. That's how fast the boat is going. Okay, when it talks about bearing, when it talks about the course, it's from north. So when we are talking about 53 degrees, we're talking about this angle right here. This is north because it's directly up. 53 degrees is 53 degrees from north. So that is 53 degrees away from north. Okay, then our boat travels a little bit. And then we get to a big old turn, and we're going to turn our boat 143 degrees from north. So we took this, we measured on a compass, we said 143 degrees from north would be here, so we turned our boat.
Go back home.
No, we're not going back. This is home. So we went this way, and then we went this way. Are we at home?
I want to go back home.
Good thing you want to go back home, which is how we're going to solve this problem. We want to know the direct distance. You gave me the best segue. We want to know this distance from Port Cleveland. Okay. Let's answer the questions first slowly. It says, what is the distance from Port Cleveland? So we have this distance. We have this distance. And we have the distance we want, which is this distance from where we are, point C, to where we came from, Port Cleveland, point A. My friends that are in physics, and I think I mentioned this earlier today, there is a formula for distance. What is the formula for distance? Rate times time. So rate would be velocity, time would be hours. So if we wanted to know the distance of the red part of this graph from A to B, we would say that this rate that we traveled at was 35 knots, and we traveled for 2 hours. So that distance is 70 nautical miles. Miles, but on water, so it's nautical.
Miss Quigley, why do you become a professor in school?
Why? It's a long story. Then we have B to C. From B to C, we want that distance. How fast were we going this whole time? 35 knots, which is a nautical mile per hour. And how long did we travel on that course? 3 hours. So that means we traveled that direction a total of 150 nautical miles. 105, sorry. So in my triangle here, this side length is 70. This side length is 105. Do you know of a way we can find the last one?
What's the term?
Pythagorean theorem. Yeah, that hasn't gone away. We still use that. So to find the side length AC, which is the distance from where we are, point C, to where we came from, Port Cleveland, point A, we're going to take the square root of AB squared plus BC squared. That's Pythagorean theorem. This is square root of 70 squared plus 105 squared which you can chunk into a calculator because, again, we're giving decimal answers here. I don't need it into square roots today because if somebody asks you how far you went, you're like, square root of 3 miles. They're like, come again? So you give it to me in actual decimals, a rounded value. 126.20 nautical miles. So that's how far from home we are if we were to fly like a bird back home. That's this distance, 126.20.
Dude, I'm a deep sea guy.
Okay, here's what we know now for the boat's bearing. The bearing is talking about the angle. We want to know this angle right here. We want to know the bearing or the angle from Port Cleveland that we are. But remember, it's from north. So not just that angle, it's going to be that angle from north is our final answer. Okay, so first things first, we need to figure out what that angle is. But if I were to just zoom in on this graph a second, or this triangle, just to give you a different picture, we're trying to find theta. We know that this side length is 70, we know that this side length is 105, and we know that this side length is 126.20. We just found that out. We also know based on our picture that this is a right angle. Doesn't look like it the way I drew it, but in our picture it's a right angle. Okay, what trig function could I use to figure out theta? We're trying to find theta. We're trying to find the angle.
Is it a Sokotoa?
It could be any of them, actually. So y'all tell me, what's your favorite one?
So.
What? I heard tangent. If we're going to find the tangent of theta, tangent is the opposite over the adjacent. What is opposite of theta? 105. What is adjacent to theta? Okay, great. Where's your variable here? Is it a side length? It's an angle. Didn't we just learn how to use trig to find angles? Oh, we're going to have to use inverse trig here to figure out what the angle is.
No.
What? Look at this all coming together. So if we solved for theta, we would need tangent to go away, right? To get theta out of tangent. What is the inverse of tangent? Don't think too hard. What is the inverse of tangent? Nope, that's the reciprocal. What is the inverse? Arctangent, also called inverse tangent. So if we take the inverse tangent of both sides, the tangents are going to cancel each other out, and I can just take the inverse tangent of 105 divided by 70.
So how do you put that into account? Oh, is it the second?
Yes. Second tangent, and then you have the fraction 105 divided by 70. We get that angle theta is what? 31 degrees, yeah. Okay.
Wait, what? I got 0.98. Wait, what am I doing? Wait.
Inverse tangent of 105 divided by 70.
Yeah, that's right.
So we found theta. If you look at your picture, is that the complete bearing from north? No. If we look at our picture, and I'm going to draw it in here, this is north. Does this angle, is that all theta? No, we got this little section here too. But guys, it's labeled in the picture. What is that bearing?
Oh, 53.
53 degrees. So our actual bearing from, what port is it? Port Cleveland is actually going to be 53 degrees plus 56.31 degrees. So our bearing, which is the angle we are from home, from north, is whatever 53 plus 56.31 is. 109.31. 109.31 degrees.
Please tell me that's the answer.
Bearing is your angle from north. So when people navigate like with a compass, they always know where north is. Like if north is this direction, the angle, like the compass would point north, and your angle would say you are 100 and something degrees away, like when you are facing this way. So what we did on this boat is when we were at point C, we said this, and we were like, okay, this is north, What's the bearing from it? What's the angle from north?
Okay, thank you.
You're welcome. We are a landlocked city. We don't understand nautical information as much as people who maybe live in like Galveston. Cleveland is Ohio, but Port Cleveland is not in Ohio. Level 3, simple harmonic motion. Again, my physics friends, this will sound familiar to you, hopefully. Simple harmonic motion is a point moving along a number line back and forth, aka in a wave. So sine and cosine, that is simple harmonic motion. What this happens where okay, let me back up for a second. These are the formulas for it. The distance from center that an object is represented by A, that's your amplitude, times sine of omega t. This is not a W. Do not call it W. It is the Greek letter omega. Okay, so A is the motion's amplitude or radius. And omega is the motion's angular velocity. So again, if you need to write that down for yourself, do not call that W. That's called omega. It's a Greek letter. Omega. In this formula, A, omega are both real numbers, and omega has to be greater than 0, so you're not going to be plugging in negative numbers for omega. The motion has a frequency of omega over 2 pi, which is the reciprocal of period. It's also the number of oscillations per unit of time. For this problem, it says in a mechanical linkage like the one shown in figure 4.94, which you can see on your page, a wheel with an 8 centimeter radius turns with an angular velocity of 8 pi radians per second. What is the frequency of the piston? So if you know anything about the way motors work, or any sort of simple harmonic motion, as the piston goes up and down, it's going to move a circle, and it's going to generate whatever. Move your tires, generate energy. This is how like water wells work. Not water wells, what is it called? Like, well, yes, also that, but yeah, like or like a water turbine where it like falls in a waterfall and it like spins the thing. Yeah, that right there, that will move the piston and generate friction or heat or whatever we're trying to generate from this machine. So this is how all of this works. If we want to find the frequency of this piston, we have a formula for frequency. The formula is right above this. It is omega over 2 pi. Omega is an angular velocity. If it's a velocity, you have something per second. In the little blurb of the equation, do you see them give us something per second? 8 radians per second. This 8 pi radians per second is omega, which means we're plugging 8 pi in for omega, which means we have 8 pi over 2 pi. What is the frequency of this piston?
4 pi.
Just 4.
Oh, yeah.
So this piston will oscillate 4 times every second. That's the frequency of the motion here. Part B says, what is the cosine equation that best models this equation, or this situation? So you're looking at the equation up there. What we want to fill in is d of t equal to a times the cosine of omega t. But the A has always represented the amplitude, and now that we're using a circle to talk about how much the point is moving up and down, it's also represented by the radius of the wheel. So what is the radius of the wheel we're using? 8 centimeters. It's going to be in the given. It's going to be given to you. So the figure is just an explanation of what's happening. So we're going to do 8 times the cosine of omega t. But what was omega again? 8 pi. Ooh, 4 is the frequency. 8 pi is the omega times t. 8 pi came from here. So remember, this is omega. It's a velocity, so if you see something per second, that's probably your omega. The last question is going to use the equation in part B. It says, what is the distance from the starting point, time is equal to 0, exactly 3.45 seconds after starting? Okay, so we need to figure out a couple things first. We need to figure out the distance that this piston is raised at time 0. But since this is a function notation formula, it's just telling me to plug in 0. So I'm going to take my formula, 8 cosine of 8 pi, and multiply that by 0. We could do this in our head, but you also have a calculator. So go ahead in your calculator, 8 times the cosine of 8 pi times 0. Now notice you have 8 pi. Are we using degrees? So switch your calculator back to radians because we were given of omega of radians per second. 8. Like I said, we probably could have done that one in our head because cosine of 0 is 1. That's just 8. Okay, well, what about how far is the piston extended at time 3.45? All that means for us is we're going to take the same equation that we just wrote, and instead of plugging in 0, we're going to plug in 3.45. So 8 times the cosine of 8 pi, use the pi button, please, not 3.14. It's going to throw you off.
I'm going to use pi on the first one.
That should be 2.47.
You don't have it?
2 decimals, please. Unless it states otherwise, we're just going to always use 2 decimals. Okay, so we want to know the distance from the starting position exactly 3.45 seconds after starting.
So we write second on the 2.47? Or do we do it?
Huh?
Do we write seconds?
That's a distance.
Oh.
So really, we're measuring centimeters.
Yeah.
In which case, if we want to know how far from starting we were, what did we start at? You're like, that's a great question, Miss Quigley. We started this. Time 0 is our start. How far were we when we started? 8 centimeters. How far were we when we measured 3.45? So we just want to subtract those and get 5.53 centimeters. That's how far from the starting position this piston is at this moment in time. Probably. They probably use circular motion to generate energy. I don't actually know about the engineering of dams. Okay, our last question for today. I know we've done a lot. A mass oscillating up and down. Ooh, oscillating. We've talked about that word before. What did oscillating mean? Something. True. Repeats. It like goes back and forth, right? We had oscillating sequences. Well, now we have oscillating functions, aka sine and cosine, because it's going back and forth. They're oscillating functions. Okay, a mass oscillating up and down on the bottom of the spring. We're assuming, for my science people, this is perfect elasticity and no friction or air resistance. It can be modeled as simple harmonic motion. If the weight is displaced to a maximum of 5 centimeters, find the modeling equation if it takes 2 seconds to complete one cycle. So if you look here, a spring. If you pull the spring down and let it go, what does it do? It bounces up and down and up and down. We're assuming it keeps doing this repeatedly for forever because there's no friction and no air resistance, so it will never stop. That's like Newton's laws, okay? We want to figure out an equation that models this situation. So we need to first decide if this is going to be sine or cosine. Here's the thing. Cosine, because we know about the way the wave works, where does it start, the regular cosine wave? 0. Where does sine normally start? 1, at the maximum, right? So if we are starting at a maximum, we're going to use cosine. And if we're starting in the center, we're going to use sine. In this situation, it says if the weight was displaced to a maximum of 5 centimeters and then we let go. Which one are we using, sine or cosine? Cosine. So we're going to fill in the cosine equation. They're the same. We want to fill in d equal to a times the cosine of omega t. Omega is working like B, like A, B, C, D's that we did before. Omega is the same. It just has a specific letter that it's used for in simple harmonic motion because of science. Okay, so we need to figure out the amplitude, and we need to figure out omega. Well, the amplitude should be easy. How far did we move it before we let go?
Yeah.
5 centimeters. That's going to be my amplitude. The omega is not so easy to find. The only other number they gave me is that it takes 2 seconds to complete one cycle. That should be a definition of a word we haven't said today that rings a bell for you. What's the vocab word we've been using when we talk about how long it takes to complete a wave? The period. So we know that the period of this function is 2. We also know, because we've studied the waves, that period's formula for sine and cosine is 2 pi divided by b. But b in this situation is omega. Okay, well, that's an equation with one variable. I can solve it. We treat it like a little proportion. We cross multiply and divide. 2 pi divided by 1 is 2 pi. 2 multiplied by omega is 2 omega. Solve for omega by dividing by 2. We're going to have pi equal to omega. So I have the number I'm plugging in for omega. I have the number I'm plugging in for A. I can write the equation. The distance of this spring can be modeled by the equation 5 times the cosine of pi times t. That would represent this spring bouncing back and forth with this starting initial value of 5 centimeters. Again, the spring's never going to stop in this situation because we're assuming no air resistance and no friction.
Wait, you're saying we don't need to solve it?
No, it just says write it.
Oh, okay.
Yeah, it just says write it.